A Canadian chemical company that hopes to sell its products in Romania may need to hire an interpreter to communicate with potential customers. But the interpreter does not need to translate the formulas of any chemicals. That is because all countries use the same chemical symbols to represent elements and compounds, even when the name is different. For example, the same symbol Fe represents the element that people call iron in Canada, FeR in France, and FiER in Romania. A chemist in any country can identify the contents of the bottle in Figure 1. Figure 1, ammonium nitrate, NH4NO3, 80.04. Chemical symbols. The alchemists in the Middle Ages were among the first to recognize that it would be convenient to represent chemical substances using symbols. A circular chart of symbols developed in China in the 13th century linked the elements to a cycle of space and time. Another system of symbols of elements and compounds was devised by the English chemist John Dalton in 1808. He represented elements as circles with letters or designs inside them, but scientists found that Dalton's system was difficult to use. These symbols are compared in Figure 2. Figure 2, no caption, but Figure 2 has two parts, Dalton's symbols on the left and alchemist symbols on the right. For instance, hydrogen is a circle with a dot in the center. Nitrogen is two semicircles put together. Today, a common set of symbols for elements is accepted around the world, even though some names may vary. A chemical symbol is an abbreviation of the name of an element. Some symbols are shown in Table 1. Table 1 has the classic symbols that we use today, no caption. Aluminum is Al, bromine Br, calcium Ca, etc. The names and symbols for elements come from many sources. Hydrogen comes from the Greek word for water former. Mercury was named after a Roman god, but its symbol Hg comes from the Latin word hydrogerum for liquid silver. Sodium was named for sodinum, a headache remedy, and its symbol Na comes from the Latin word natrium. Notice that a single letter symbol is always capitalized, and that the first letter of a two-letter symbol is capitalized while the second letter is not. Chemical formulas. Just as single symbols are used to represent elements, combinations of these symbols are used to represent compounds. A chemical formula is the combination of symbols that represent a particular compound. Table 2. For instance, sodium bicarbonate, baking soda, bi means hydrogen, NaHCO3, calcium carbonate, which is chalk, CaCO3, sodium nitrate, which is a fertilizer, NaNO3, etc. The chemical formula indicates which elements are present in the compound and in what proportion, as shown in Figure 3. That's water is H2O, it's two hydrogens for every oxygen. Methane, which is CH4, there's one carbon and four hydrogens. And hydrogen peroxide, there are two hydrogens for every two oxygen. Each chemical symbol in a formula represents an element. If only one atom of an element is present in a compound, no number is included. If there is more than one atom of that element in the compound, the symbol is followed by a number written below the line, in other words, a subscript. This number, called a subscript, tells how many atoms of that element are present in one molecule. For example, the formula of water is H2O. Tells you that the elements are present in a ratio of 2 atoms of hydrogen to 1 atom of oxygen. The formula for sodium bicarbonate, NaHCO3, tells you that the elements are present in a ratio of 1 atom of sodium to 1 atom of hydrogen to 1 atom of carbon to 3 atoms of oxygen. Understanding concepts. Why are symbols useful in describing chemicals? That's number 1. I'll leave that to you. 2. What are the symbols for the following elements? I'll also leave that to you. Number 3. Write a chemical formula for the following: a molecule of hydrogen gas that is made up of 2 atoms of hydrogen. I'll leave that to you. A molecule of propane gas that is made up of 3 atoms of carbon and 8 atoms of hydrogen. I'll also leave that to you. Number 4, for each of the compounds in Table 2, state the number of different elements present and the number of atoms of each element. What is the total number of atoms in each molecule? Number 5, molecules of nitrous oxide used by dentists as an anesthetic contain 2 atoms of nitrogen and 1 atom of oxygen. Write the chemical formula for nitrous oxide. Making connections. Number 6. Research a common use of each of the following pure substances: helium gas, sucrose, acetone, tartaric acid, and propane. Number 7, prepare a chart describing each substance above, where it is used, chemical formula, and the number of atoms in each type of element in the compound. Atoms, molecules, and the atmosphere. Slowly breathe in a lungful of air. As you do, think about the billions of molecules that you are inhaling. Air is mostly nitrogen and oxygen, but you are breathing in a mixture that contains other gases as well. In this section, you will learn about some of the gases found in air. Nitrogen, N2. 2 atoms of the element nitrogen combine to form a molecule of the gas nitrogen, figure 2A. Nitrogen makes up approximately 80% of the atmosphere. However, under certain conditions, such as in a car engine, nitrogen reacts with oxygen to form very toxic nitrogen dioxide, a very toxic red-brown gas. Nitrogen dioxide in low concentration causes the yellow haze of air pollution you may have seen in some cities. Argon, AR. It's a noble gas. Argon atoms do not combine with other atoms to form molecules. As a result, argon gas is composed of a single atom of argon. Almost all the argon in the atmosphere has leaked out from inside the Earth. This gas is completely harmless and quite useful, especially for filling electric light bulbs and fluorescent tubes. Oxygen, O2 and O3, that's figures 2, C, and D. Atoms of the element oxygen can combine to form 2 different molecules. The more common of these contains 2 atoms of oxygen. This is the form that makes up about 21% of the air you breathe and is what we call oxygen gas. Almost all organisms need oxygen to survive, as it is used in cellular respiration. The less common oxygen molecule, called ozone, O3, contains 3 atoms of oxygen. That's figure 2D. Ozone is formed naturally in the upper layers of the atmosphere. It is very important to life on Earth because it absorbs most of the ultraviolet radiation from the sun. If all this radiation reached the surface of the Earth, it would harm all living things exposed to it. Unfortunately, air pollutants such as chlorofluorohydrocarbons, CFCs, have been destroying the ozone layer at an alarming rate. Worldwide measures to stop this pollution have begun, but it will be years before the risk to the ozone layer is past. Because of damage to the ozone layer, more ultraviolet light is now reaching Earth's surface. Ultraviolet light damages skin. As a result, scientists now encourage people to protect their skin with clothing or sunscreen when they go out in the sunshine. Again, this book is about 20 years old, and the problem with the ozone layer is better than when this book was published. While the layer of ozone several kilometers up in the upper atmosphere is necessary for life, ozone at ground level is hazardous to living things. It can damage plants and cause respiratory problems in people and other animals because it reacts with lung tissue. It is produced when certain gases, produced mainly by vehicles, react with each other and with the more common O2 molecule, carbon dioxide and carbon monoxide. 2 atmospheric gases contain only atoms of carbon and oxygen, figure 3. Carbon dioxide molecule is A, and B is carbon monoxide. 1, carbon dioxide is necessary for life on Earth. The other, carbon monoxide, is extremely poisonous to vertebrate animals. When fossil fuels burn, the 2 main products are carbon dioxide and water. However, if there is a shortage of oxygen during combustion, carbon monoxide is also produced. How can the supply of oxygen be limited? If you burn propane indoors, for instance, in a gas barbecue or heater, you might use up the oxygen from the air in the room. The same might happen if you run an automobile engine in a closed garage. The carbon monoxide molecule, CO, is similar to the oxygen molecule, O2. This similarity makes carbon monoxide poisonous. When carbon monoxide molecules enter the lungs, the body's red blood cells treat CO molecules as if they were O2 molecules. Instead of oxygen, the cells carry CO through the body. The cells of the body are starved of the oxygen they need. Death can result. In order to prevent accidental fatalities due to carbon monoxide poisoning, many municipalities are passing bylaws that require CO detectors in every home. Carbon monoxide simply outcompetes oxygen for a place on the hemoglobin. Carbon monoxide is produced by the incomplete combustion of the fossil fuels, gas, oil, coal, and wood used in boilers, engines, oil burners, gas fires, water heaters, solid fuel appliances, and open fires. When carbon monoxide is present in the air you breathe into your lungs, it attaches itself to the hemoglobin. The bond between hemoglobin and carbon monoxide is 250 times stronger than oxygen. In the lungs, carbon monoxide attaches to red blood cells in place of oxygen. You can see the carbon monoxide and oxygen being inhaled by the person on the left. The oxygen and carbon monoxide are inhaled, and then oxygen and carbon monoxide enter the blood. The normal oxygenation is above on the right, and the carbon monoxide poisoning is on the lower right. the carbon monoxide simply outcompetes the oxygen for a place on the hemoglobin. Understanding concepts. Identify as element or compound each of the following molecules. Carbon dioxide is a molecule made of carbon and 2 oxygens. Carbon monoxide is a molecule made of 1 carbon and 1 oxygen. Oxygen is an element, but it's also a molecule, O2. Ozone is a molecule, O3, and nitrogen is both an atom and a molecule. Atom N and molecule N2. 2. Carbon dioxide and carbon monoxide contain 1 carbon and oxygen. Which of these molecules is dangerous to breathe? Why is it dangerous? I'll leave that to you. 3A. How is ozone formed at ground level? I'll leave that to you. B. What effect does this ozone have on living things? 4. If humans and all other animals are constantly producing carbon dioxide and it is a fairly stable gas, why does it make up only a tiny percentage of the Earth's atmosphere? I'll leave that to you. Exploring. People with some diseases, such as emphysema, are given air with an increased percentage of oxygen. Find out what proportion of oxygen is in this air. What safety precautions would you advise for people near the patient? Create an information brochure. 6. Visit an automotive service center. What device is used to prevent any buildup of carbon monoxide inside the garage? That was A. B. How is fresh air brought into the garage? C. How would fresh air reduce the amount of carbon monoxide produced by cars? Reflecting. 7. Would you make any changes to the list of substances that you produced at the beginning of the chapter? Names and formulas for compounds. You have learned that chemical formulas can be written to represent compounds. But how do we know the proportions of each element? For example, we may know that table salt, sodium chloride, contains the elements sodium, Na, and chlorine, Cl. But is the compound NaCl or NaCl2 or Na2Cl or some other formula? The key is in knowing how many atoms combine. Some of the basic principles are summarized in Table 1. Table 1, how elements combine. Metals combine with nonmetals in many compounds. Rule 2, write the name of the metal first and the nonmetal second. Change the ending of the nonmetal to IDE. Each atom has its own combining capacity. Rule 5, atoms combine so that each can fill its combining capacity. After performing many experiments, scientists discovered patterns in the ability of different elements to combine to form compounds. They analyzed how many atoms of each element were present in a molecule of each of the compounds. This ability to combine with other elements is called the combining capacity. Combining capacity is similar to the number of connections that an atom can make. Scientists have given a numerical value to the combining capacity of each metal or nonmetal to explain the compounds that they form. For example, both sodium and chlorine were assigned a combining capacity of 1. Sodium chloride has the formula NaCl. It contains 1 atom of sodium for each atom of chlorine. Calcium chloride has been found experimentally to have the formula CaCl2. Each of the chlorine atoms has a combining capacity of 1. So the combining capacity of calcium must be 2. You can better understand this idea by thinking of the work you have done with models. Aluminum has a combining capacity of 3. That is, it needs to make 3 connections. Each chlorine atom only needs to make 1 connection. Thus, when aluminum combines with chlorine, the resulting compound is aluminum chloride, AlCl3, a compound used as an antiperspirant. Tables 2 and 3 list the combining capacities of metals and nonmetals. Let's look at that quickly. Table 2, so you have aluminum, barium, calcium, magnesium, potassium, silver, sodium, and zinc, and the combining capacities. Aluminum is 3, barium is 2, calcium is 2, magnesium is 2, potassium is 1, silver is 1, sodium is 1, and zinc is 2. Bromine, chlorine, fluorine, and iodine both have a combining capacity of 1, oxygen and sulfur 2. You can use these numbers to predict the chemical formulas of the compounds that such elements form. Sodium bromide, figure 1A, 1 sodium and 1 bromine, because it's going to be 1 and 1, used in photography, is made of sodium and bromine. Each of these elements has a combining capacity of 1. Thus, the chemical formula is NaBr. The compound calcium oxide, figure 1b, or lime, is made up of the elements calcium and oxygen. For both of these elements, the combining capacity is 2. Thus, 1 atom of calcium can combine with 1 atom of oxygen. The chemical formula of calcium oxide is CaO. If the combining capacities of the elements are different, then the numbers of the atoms are also different. For example, calcium has a combining capacity of 2, chlorine has a combining capacity of 1. Therefore, in the compound calcium chloride, figure 1c, 1 atom of calcium combines with 2 atoms of chlorine. The chemical formula of calcium chloride is CaCl2. Aluminum has a combining capacity of 3, and oxygen has a combining capacity of 2. Therefore, in the compound aluminum oxide, figure 1d, 2 aluminum atoms must combine with 3 oxygen atoms. The chemical formula of aluminum oxide is Al2O3. Metals with more than 1 combining capacity. Some metals have different combining capacities in different compounds. You can see in Table 4 that lead, copper, tin, and iron all have more than 1 possible combining capacity. In naming compounds of these metals, their combining capacity is shown in Roman numerals following the name of the metal. For example, there is a compound named iron 2 oxide, and that's the way you say it, iron 2 oxide, and another named iron 3 oxide. Similarly, there are 2 compounds of copper and oxygen. Understanding concepts. What does the term combining capacity mean? That's number 1. Number 2, elements can be classified as metals or nonmetals. Which elements change their names when they form compounds? Explain with an example. What are the names of the following compounds? Calcium chloride, used in bleaching powder and for melting ice. Calcium oxide, used in plaster for construction. Copper 1 chloride, used to make red-colored glass. Potassium iodide, added to iodized table salt to prevent a condition called goiter. Silver 1 chloride, used in photography. Use the values for combining capacities shown in the tables to write chemical formulas and draw hook and ball diagrams for A, sodium fluoride, B, magnesium fluoride, C, potassium bromide, D, zinc oxide, E, silver oxide, F, aluminum fluoride, G, aluminum sulfide. 5A. Tin forms two different compounds with chlorine. Tin 2-chloride and tin 4-chloride. Build a simple model of each compound showing tin's combining capacity. Give the names and formulas of the two compounds that tin could form with oxygen. Exploring. How do sodium chloride and calcium chloride melt ice? What are the advantages and disadvantages of each compound? Why is urea sometimes preferred to either of these compounds? Plant nutrients and fertilizers. A farmer looks at a vegetable crop about to be harvested, figure 1. Farmers need to make decisions about how to increase the amount of vegetables or fruit that their fields can produce. The growing season has been a good one with lots of sunlight, warm weather, and rain. But the farmer has made some deliberate, important decisions to increase yield and make the plants as healthy as possible. The plants grow in soil that has been carefully enriched by the addition of chemical substances. These substances added to the soil to help plants to grow are called fertilizers. Why have fertilizers been added? What chemicals are in each type of fertilizer? How does the farmer choose which kind of fertilizer to use? What plants need from soil? Plants take in and process chemical compounds called nutrients in order to grow. The plants take in water through the roots and carbon dioxide from the air through openings in the leaves. Using energy from the sun, they combine these compounds in a chemical change called photosynthesis to produce sugars and oxygen gas. This change can be represented by the word equation: carbon dioxide plus water in the presence of chlorophyll and sunlight yields sugars and oxygen. Table 1 shows that all living things need elements other than carbon, oxygen, and hydrogen. Table 1, nutrient elements essential for plants. Elements needed in large amounts: carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium. In medium amounts: calcium, sulfur, magnesium, copper, zinc, chlorine, and cobalt. In tiny amounts: iron, manganese, boron. That's iron, manganese, and boron. Manganese is Mn. Sounds kind of like magnesium, but it's manganese, Mn, on the periodic table. These additional nutrients are dissolved in the water that the plant takes in through its roots. Some of the nutrients come from minerals in the soil, and some from decomposing plant and animal matter. As the plants grow, they use more and more of these nutrients, and the soil becomes less rich in the elements that plants need. Nutrients can also be lost as rainwater moves down through the soil to the water table, taking water-soluble nutrients with it. The farmer must then decide how to replace these elements. One method is to remove just the useful part of the plant, leaving most of the plant to be plowed back into the soil. Corn is often harvested in this way. Another choice is to add fertilizer to the soil to put back the elements that plants need, figure 2. The crop on the left was given chemical fertilizer. The one on the right was not fertilized. The fertilizers can be either chemical or organic. Don't be confused by the names. Organic fertilizers have some of the same chemicals as chemical fertilizers, but they are produced naturally. Chemical fertilizers. The most important nutrient elements after carbon, hydrogen, and oxygen are nitrogen, N, phosphorus, P, and potassium, K, figure 3. The number rating on the bag of fertilizer indicates, in order, the ratios of nitrogen as nitrate, phosphorus as phosphate, and potassium in the mixture. But these elements have to be absorbed as compounds, not as elements. In a chemical reaction called nitrogen fixation, a few plants are able to change nitrogen from the air, N2, into compounds called nitrates. For example, ammonium nitrate or ammonium nitrate, NH4NO3. The nitrates can dissolve in water and be absorbed through the roots. Plants absorb phosphorus in the form of compounds called phosphates. For example, sodium phosphate, Na3PO4. Calcium phosphate is human bone. Potassium forms many compounds that are soluble in water. It can even form compounds with nitrate or phosphate. Most potassium salts are soluble in water. Potassium phosphate, K3PO4, and potassium nitrate, KNO3, other sources of nutrients are summarized in Table 2. Table 2, some chemical sources for major plant nutrients. Carbon dioxide, hydrogen from water, oxygen from the water, nitrogen from ammonia, NH3, ammonium nitrate, NH4NO3, and urea, N2H4CO. Phosphorus, calcium dihydrogen phosphate, Ca in parentheses H2PO4 with a 2 on the outside. Potassium chloride, KCl. Chemical industries mix these compounds together in very precise amounts depending on the particular crop or the time of year that the fertilizer will be spread on the fields. These 3 nutrients are so important that typically fertilizers used on the farm or in the home garden are described by 3 numbers corresponding to the percentages of these 3 elements in the mixture. For example, 15-10-5 fertilizer contains 15% nitrogen as nitrate, 10% phosphorus as phosphate, and 5% potassium. Organic or chemical farming. When the farmer wants to add fertilizer to the soil, there are 2 choices, natural or chemical. The farmer can choose a natural fertilizer such as manure or compost. That's organic. Natural is organic. Such fertilizers are often called organic fertilizers because they are natural fertilizers, natural material produced by living organisms. Many people favor this kind of fertilizer because it recycles materials that otherwise might be wasted. Such fertilizers can also save energy because the manure or compost may be produced on or near the farm and will probably not require transportation over long distances. A disadvantage of using natural fertilizers, apart from a rather powerful smell, is that farmers cannot know the exact amounts of nutrients that they are adding. Very large farms also may have difficulty obtaining enough natural fertilizer for their needs. Organic farmers not only use natural fertilizers, but also avoid chemical pesticides and herbicides. Still, most farmers choose chemical fertilizer that are produced by industries. They can include exact amounts of any individual nutrient so that the farmer can deliver just the right mixture of nutrients to the particular field or crop. These fertilizers are often packaged conveniently and are so concentrated that a small amount of chemical fertilizer can deliver a large amount of nutrients. Chemical fertilizers can also be mixed with water and delivered through pipes or sprayed over large areas of fields, as in Figure 4. Fertilizer spreaders are used by farmers to add nutrient elements to the soil. Table 3, percentage of nutrients removed by different crops. Wheat, for instance, bread, that's nutrient element. Nitrogen 1.7, phosphorus 0.3, potassium 0.5, calcium 0.05, magnesium 0.1, and sulfur 0.1, etc. You can see that quite clearly that wheat removes a lot of nitrogen from the soil relative to grass or simply potatoes. Understanding concepts. 1. What elements are needed in large amounts by plants? Number 2, what are the major natural resources of nutrients for plants? Number 3, use Table 2 to state what types of atoms and how many of each are found in a molecule of urea and calcium dihydrogen phosphate. Making connections. 4. Plants take in nitrogen, phosphorus, and other atoms through their roots and use the atoms to build roots, stems, and leaves. The following questions are based on Table 3, which shows the percentage of nutrients removed from the soil in a growing season by different crops. A. Which element is most used up as crops grow? B. Which crop uses potassium, K, at the greatest rate? Which crop would require a fertilizer mix with the most calcium? Exploring. Find out from a fertilizer supplier which fertilizer mixtures are used at different times of the year and why. For example, one mixture might be used in the fall to promote strong root growth to help the plant survive the winter. Number 6, consider the following statements. Chemical fertilizers are preferable to organic fertilizers. Decide whether you agree or disagree with this statement and write a persuasive essay, putting together as many arguments as possible to support your point of view. Use arguments and evidence from this text or from research. Consider examples from large and small-scale farming, city parks, home gardening, or any other situation where fertilizers are used. Metal extraction and refining in Canada. Think of all the materials around you that are made of metals. Very few of these metals occur naturally as elements. Gold nuggets are still panned from stream beds, and silver and copper are often found as elements. But most metals in nature are found in the form of compounds because they combine very readily with oxygen, sulfur, or other elements. These compounds are called minerals. Table 1. Types of minerals. Element: silver, gold, platinum. Mineral name: silver, gold, platinum. And that's what it looks like. Calcium is in limestone. Aluminum in bauxite. Lead is in galena. Mercury is cinnabar. Iron is magnetite. Copper is malachite. Okay. For example, most iron mines produce the compound iron oxide, Fe3O4, rather than the element iron. However, minerals are rarely found as pure substances in the ground. They are mixed with many less useful compounds in rocks called ore. That's figure 1. Figure 1 shows a map of Canada with nickel, zinc, and iron deposits around. You can see that for yourself. How are minerals separated from the rest of the ore? How are elemental metals produced from the mineral compounds? Figure 1, mining of metals occurs across Canada. Some of the most important metals produced in Ontario are nickel, zinc, and iron. Metals in history. In prehistoric times, people perhaps learned by accident how to make metals from minerals. Previously, they used stone and bone tools to plant crops, hunt animals, and chop wood. Around 3500 BC, people learned how to smelt copper, that is, to react the copper and draw it out of the other materials in the copper ore in a chemical change. Centuries later, when copper and tin were mixed together in a process, the result was a much harder, more flexible metal alloy called bronze. Over the centuries, other new metals were produced, each having new advantages of hardness, durability, or flexibility. Figure 2. Figure 2, this furnace called a tatara is the type used to make samurai swords. Making steel was a complex technology developed early in Japan's history. At a time when there was no written language, the process of sword making became part of a ritual, which was passed from generation to generation. Mining and metallurgy. Today, metal production is one of the most important natural resource industries in Canada. Mining and metal refining employ thousands of people across the country and contribute billions of dollars to the economy. Figure 3. Large ore carriers are used to remove nickel ore from this mine in Sudbury, Ontario, for further processing. Canada is the world's top exporter of minerals such as iron, nickel, copper, aluminum, and zinc. The technology of separating a metal from its ore is called metallurgy, figure 4. Iron metal is produced at temperatures of over 1,000 degrees Celsius in a blast furnace. It requires a knowledge of both physical and chemical properties of minerals and metals. Preparing the ore involves crushing the rocks and separating the desired minerals from waste materials, often clay and other minerals. Magnets are used to separate the magnetic elements such as iron. Gold and silver are dissolved in mercury to form alloys, which can be separated from the rocks. Producing the metal from its minerals involves chemical changes. In iron production, the mineral iron oxide reacts with carbon monoxide to produce iron metal. This can be represented by the word equation iron oxide plus Carbon monoxide yields iron plus carbon dioxide. Metal production has many environmental implications. For example, the extraction of lead from galena involves 2 stages. The first step is to change lead sulfide into lead oxide. A second, easier chemical reaction changes lead sulfide to pure lead. An environmental problem lies in the first reaction, which is shown by the word equation. Lead sulfide plus oxygen yields lead oxide plus sulfur dioxide. Sulfur dioxide is one of the main sources of acid rain. Industries try to remove this gas from smokestacks in a process called scrubbing instead of releasing it into the atmosphere. Purifying the metal involves removing any impurities from the metal. The metal can be distilled if it has a low boiling point. The metal is heated to evaporate it from the impurities. Electricity can also be used in a process similar to the electrolysis of water. Using metals to make alloys. Many metals are more useful if they are melted and mixed with other metals to form alloys, Table 2. Stainless steel is a solid-solid solution of 70% iron, 20% chromium, 10% nickel used in cutlery. Plain steel is simply 98% iron, 2% carbon. And high-strength steel is 95% iron, 2% manganese, 1% carbon, 1% chromium, and 1% other materials used in steam turbines. Changing the composition of the mixture, even by tiny fractions, can have dramatic effects on the properties of the alloy. For example, hundreds of different mixtures of elements are used to produce various steels. Solder is an alloy of lead and tin that melts at a lower melting point than either the pure metals, Figure 5. A technologist uses soldering iron to align protective coatings over circuits in the manufacture of flexible electronic circuits. Electronic technologists, plumbers, and electricians melt it to join metal pieces such as electronic components, pipes, or wires. Understanding concepts. 1. Design a concept map on mining. Begin with the word element. 2. Using Table 1, identify the elements in each of the following minerals: bauxite, cinnabar, and galena. 3. What are the chemical symbols for the metals that can be obtained from the following minerals? A, limestone, B, magnetite, and C, malachite. 4A, what are 3 steps in obtaining a metal from its ore? B, which steps include a 1, I, physical change, 2, chemical change. 5, using the word equations in the section as a guide, complete these word equations for metal production. Lead oxide plus carbon monoxide yields lead plus what? Zinc sulfide plus oxygen yields what? Question mark. Plus sulfur dioxide. Making connections. What practical advantages would the discovery of bronze have given people? 7. Why are metals mixed together to form alloys? What are the environmental implications? Exploring. 8. Research the methods used to obtain one of the following elements in Canada: nickel, copper, iron, zinc, gold, silver, lead, or uranium. Use a variety of sources and media and prepare a presentation. 9. Recycling of metals is an issue that presents many questions.
What metals are recycled in Canada? What elements are in short supply and should be recycled? What problems are associated with recycling? How does the cost of recycling compare with the cost of producing a metal from the ground? What pollution issues are addressed in recycling? Develop your own research project on some aspects of metal production and recycling. 10. A car exhaust pipe made of stainless steel corrodes much more slowly than one made from normal steel. However, it costs more than twice as much as a normal exhaust pipe and is more difficult to attach to other metal components. How would you decide whether or not to use a stainless steel exhaust pipe? What factors would you consider? If you can, talk to your local muffler repair shop about these questions and report your findings.